let's get started. Hello, everyone. My name is Christina Wolford. I am the Director of Education here at the International Biometrics Society. I would like to welcome you to today's Journal Club. Before we start, I would like to go over a few housekeeping rules. So we ask that you keep things simple. We don't like to be too technical in the Journal Club. Keep it short, speak slow and clearly, be constructive, build the discussion in a positive way. We always want to respect others. Raise your hand if you would like to speak, and we will address your questions and concerns in the chat box. Mute your microphone. As you can see, I have already taken care of that for you. The paper and other supporting documents are available in your registration email from me. This recording will also be made available afterwards. So we have to remember, if we don't mute our microphone, all those comments will be recorded. I would like to now hand off the presentation over to Dr. Jim Todd, who's the Journal Club organizer and chair. Jim, if you would like to go ahead.
Lovely. Thank you very much, Kirsty, for your introduction, and welcome to everybody here. Thank you. We hope the Journal Club is informative and useful, and as you know, we run it every 2 months. The opportunity is to network and interact and to ask questions about new topics, discussing new statistical issues. So we're pleased to have John Rice this time joining us to present his paper, and then I'll be leading the discussion on the paper. So make sure that you get your questions in for later. Feel free to engage with those discussion later and think about what we can do with the methods and the statistical methods that John is going to present in our work. So without further ado, I shall hand this over now to John Rice to present his paper, Regularity of a Renewal Process Estimated from Binary Data. Thank you. Over to you, John.
Okay, thank you, Jim. And thank you all for joining us this morning. I'll be discussing our work on estimating parameters associated with the renewal process from longitudinal binary data, which is based on work I did as a postdoc with Strawderman. So first, what is regularity? This comes up in many areas of biostatistics, including annual physicals, screening or testing for HIV and cancer, dental visits, and adherence to treatment regimes for chronic conditions such as asthma. I think we all have an intuitive idea about what this means, but statistical treatments have been somewhat limited. One of the problems is that the term regularity is often used to imply certain levels of frequency, which has been the case for much of the HIV testing literature. Another difficulty is that different forms of data require different methods for measurement or estimation of regularity, however we've defined it. But I'll get into more specifics about that later in the presentation. So some definitions. I want to emphasize the distinction between frequency and regularity right off the bat here. So frequency is how often an event occurs, and it's inversely related to the mean time between events. So for this reason, we refer to this as the first moment property. And that's in contrast to regularity, which is related to the variability in space in between events. So we refer to this as the second moment property. Just to give an idea of what I mean by the distinction between frequency and regularity, here are some figures showing simulated event histories for 5 hypothetical individuals with the same frequency of events but different levels of regularity. Each panel has an average time between events of 3 time units. The most irregular in the left-hand panel is characterized by both clustering of events and large gaps between events. The middle panel is actually 5 Poisson processes, where the interevent times are exponentially distributed. And the right-hand panel depicts a more regular process with closer to deterministic spacing between events. Sorry, I've advanced the slide, but it doesn't seem like it's... Here we go. I just want to briefly describe our motivating data set now before we get into the methodology. The original data was collected in a study of men who have sex with men, or MSM. And our interest is actually in data collected as a response to a question of whether or not the subject had self-tested for HIV in the previous 2 months. And this was asked longitudinally over the course of 1 year. So the authors of the original study wanted to determine if text messaging was more effective at retaining subjects in the study relative to online follow-up. The hypothesis being that SMS or text messaging was a more direct way of getting in touch with subjects and so should be associated with improved adherence or outcomes. But again, we are interested in determining the effect of the intervention on frequency and regularity of self-testing. So we are modeling our events as a renewal process, which generalizes the Poisson process to allow non-exponential inter-event times, which allows the coefficient of variation, or CV, as I'll refer to it, to be less than or greater than 1. With the exponential distribution, it's restricted to be equal to 1. And the CV, as a reminder, is the ratio of the standard deviation to the mean, and this refers to the time between the distribution of time between events. We're going to focus specifically on the gamma renewal process, which has been used in the past to model course and recurrent events. There's a paper by Winkleman here. And by coarsened, I mean that the exact event times are not observed. So one way that can happen is if only the count of events over a certain time period is recorded, which was the situation Winkleman was dealing with. And he derived some important results relating the CV of the inter-event times to over or under dispersion of the resulting counting process. Specifically, a CV greater than 1 implies over dispersion, and a CV less than 1 implies under dispersion. And this is relative to the Poisson process. And I'd just like to point out the kind of convenient feature of the gamma distribution is it has a very simple relationship between its shape parameter and its coefficient of variation, in the sense that the shape parameter is equal to the inverse square of the CV. So this figure is meant to give an idea of the shapes of gamma densities that are possible for different values of the shape parameter. You can see that as the CV decreases, the density becomes more concentrated about the mean, which is 3 for all the densities shown here, as it was for the simulated event histories I presented a few slides ago. As the CV increases, the density becomes more spread out with a mode at 0, which contributes to both the large gaps and the clustering of events that was observed for the simulated event histories in the irregular panel. So to describe our regression model, it's convenient to parameterize the gamma distribution in terms of its mean and shape rather than the traditional rate and shape, and I have the density here in that parameterization. So for fixed mu, or mean, increasing the shape parameter causes the variance of the inter-event times to go to 0, which would induce a degenerate distribution at mu. So that would be a deterministic spacing of events. So we're modeling both the mean and the coefficient of variation, or shape parameter here, as a function of covariance. And I've written it here as Z being in both models, but this could be more general. We could have different covariance in each part of the model. So the data we observe, as I said, is actually coarse in the sense that we don't get to observe the exact event times. We do assume that each subject experiences events according to an independent gamma renewal process, and we define the difference in counts between time points tj-1 and tj as delta nij. We assume we have k intervals, which don't necessarily have to be equally spaced, but for what we're doing, our motivating example, they are, and for the simulations I'll present, they are as well. So what we're observing, though, is actually more coarse than count data, because we're only observing a binary indicator that's equal to 1 if there were any events during that interval. So if delta nij is greater than 0. So if we did have access to the exact event times, we could use a point process likelihood based on the IID property of the renewal process to estimate gamma and beta. But, again, as I said, we're in this coarse data setting, so estimation is more difficult. We've we're going to present two strategies for this. First is we could just use the time to the interval containing the first event to define this discrete survival likelihood function. This should be more robust since it doesn't rely on assumptions about the time between events. However, it disregards information on later events, so it could lose some efficiency. The alternative approach is to use the forward recurrence time distribution to define a quasi-likelihood, which could gain efficiency because we're using all the available data. But since we aren't modeling the full joint distribution of the indicators, we don't have a true likelihood, so there could be efficiency losses there. It's also computationally a bit more difficult to work with the forward recurrence distribution relative to the discrete survival likelihood, which is just based on the CDF of the inter-event times. So I just want to describe now in a bit more detail how we relate the forward recurrence distribution to our observed binary indicators. The expectation of Yij, which is our observed binary data, is equal to the probability that there's at least one event between Tj minus 1 and Tj. And this is equivalent to the probability that forward recurrence time at Tj minus 1 is less than the length of the next interval, essentially. And we can use this to construct estimating equations for our model using a computational algorithm due to Arnold and Groeneveld that's based on discrete approximations. So just some brief results from some simulation studies that we conducted to compare performance between the forward recurrence estimating equations and the discrete survival likelihood methods. These simulations involved log normal distributions for the shape and the mean parameters of the gamma distribution. So this is a continuous covariate scenario. We fixed the sample size at 500 individuals, so 500 independent renewal processes were simulated. And this is similar to our motivating data set where we had about 600 subjects. We varied follow-up time, which is denoted tau, and number of observation intervals. But we kept the intervals of equal size. So the methods we are going to compare are, as I said, the discrete survival likelihood, which is possibly more robust but less efficient, and the forward recurrence estimating equations. And the partition numbers have to do with the discrete approximation we're using, with more partitions being associated with longer computation times, but also more accuracy. So we thought it was important to get an idea of how much we could get away with in terms of faster computation without losing too much in terms of accuracy. So this is the mean square error of the shape parameter estimate, so gamma naught and gamma 1, when we have 4 observation intervals. I'm just focusing on the shape parameter because we're interested in regularity here. But we also looked at the mean parameter estimate. So the MSE is considerably lower for both versions of the FR method than for the DS method, which is reflective of the accuracy that we gain by using all available data. There's an interesting U-shape here that you can see for gamma 1, which is a result of the symmetry of the Bernoulli distribution. As the length of the observation interval increases, more intervals will contain at least one event. But on the other hand, for shorter intervals, fewer intervals will contain any events. So in both cases, there's a loss of information because you're sort of either maxing out on zeros or maxing out on ones. This is in contrast to if we were able to observe even the less coarse count data, where increasing the length of the interval would always increase the information available because there's no sort of cap on the number of counts or the count that you can observe. So these are the simulation results for the scenario of 6 observation intervals, which is actually what we have for our motivating data set, where the story here is broadly similar to the previous slide, but the main thing to note is the decrease in MSE for both parameters relative to the k equals 4 case, which shows the increase in estimation efficiency from having more intervals available, even when the total follow-up time is fixed as it is along the x-axis here. So now I'm going to talk about the motivating data analysis. And it looks like the slide hasn't advanced, but sorry, just having some technical problems here.
Hey, John.
Yes.
Which slide are you want to be on?
I think we're okay.
Okay.
I'm on the study design slide.
I'm sorry?
I'm on the study design slide. Is that
everybody
sees that?
Yep.
Okay, great. So I'm going to describe the analysis of the motivating data example from the HIV self-testing data set. So recall that we want to investigate whether the intervention had any effect on the regularity of self-testing for HIV. We had about 300 subjects in each randomized arm available for analysis. The study period was divided into 6 intervals of 2 months each, so 8 to 6 here. And these are of equal length, as I said. And the outcome of interest, YIJ, is equal to 1 if the subject reported any HIV self-test during each interval. And the missing data on the outcome was assumed to indicate that no self-testing had occurred. And from the perspective of policy or public health, this is a conservative assumption because we're not going to overestimate the rates of testing. So our modeling strategy, we did fit regression models with more demographic covariates that included things like education and race, but none of these were significant, so I'm only going to present the results for models with the treatment variable as a covariate. And we want to test the primary hypothesis that gamma 1 is equal to 0, which would mean that the groups have the same level of self-testing regularity. So in that case, the null hypothesis is that the treatment does not affect regularity of self-testing. Kind of secondary interest, we want to test whether either group deviated from Poisson level regularity. And to look at the fit of the models, we plot the empirical mean of binary indicators in each treatment group and interval along with the mean predicted by the model, which is given here by the expression G. So we looked at, we used both the discrete survival and the forward recurrence methods to obtain parameter estimates. And just a summary of the results here. Both methods lead us to conclude that there is a significant difference in testing regularity between the two groups. The online group was also found to have significantly more irregularity than a Poisson process by both methods. We did find conflicting results, however, for the SMS group, with the discrete survival method suggesting non-significant irregularity and the forward recurrence method suggesting marginally significant regularity. This slide actually just shows the estimated shape and mean parameters for each treatment group by each estimation method. The shape parameter estimates are very similar between methods for the online group, a little more different for the SMS group. The mean times between tests are considerably larger when estimated by FR as compared to DS, which seems reasonable given the DS method is ignoring later events occurring after the first interval, at least one event. So it seems like it could underestimate the frequency of testing. There's an interesting distinction between regularity and frequency here in the results. So while the SMS group was estimated to be significantly more regular than the online group, they were also self-testing less frequently. However, statistical significance was only found for the second result by the FR method. So this figure shows the how we looked at goodness of fit for each estimation method and each treatment group. So each panel is the different treatment group. And we measured accuracy by root mean square error of the predictions across all the time points. We found this to be lower for the forward recurrence method than the discrete survival method, which again is reflective of the increase in efficiency that we gain by using all the available data. So one thing to note here is that the scale of the y-axis is different between the panels, and this was to show the detail in the SMS group because they were testing at a lower rate overall, especially in the first interval. So to recap, we proposed two methods for estimation of the coefficient of variation mean of a renewal process from longitudinal binary data, one based on a discrete survival likelihood and one on the forward recurrence distribution leading to a quasi-likelihood. And this is applicable more generally than the gamma renewal process, although that's what we focused on here since it's convenient in terms of its parameterization. One of the important features of these methods is that they allow us to distinguish the effects of covariates on the frequency and regularity of the renewal process, which I've tried to emphasize is these are two different features of the testing process that I think should be treated separately. But this is our definition of regularity is not the only one possible. We've defined it by the coefficient of variation, but it's possible that it could be meaningful also to look at the second raw moment, which would kind of combine the ideas of frequency and of regularity. If coming from the perspective of more frequent testing being desirable, then if this second moment was decreased, then you'd be looking at either greater regularity or greater frequency. So it's possible that could be something interesting to look at in its own right. Just briefly, some extensions we want to consider in future work. One simple option is to look at some other parametric distributions for the inter-event time, which could be log normal or Weibull, which would be a pretty simple extension. But if we wanted to extend it to a three-parameter family, perhaps possibly to get a better fit to the data, this might be more complicated because it's potentially the relationship between the three parameters and the mean and coefficient variation could be more complicated. One of the nice things about the gamma distribution that we've used is that it has that simple relationship between the coefficient of variation and the shape parameter. More generally, we would like to use Winkleman's result relating with CV to monotone hazard rates, but it's not entirely clear how we could apply that directly with binary data. And some of the other assumptions of the renewal process that we'd like to weaken as well would be the identically distributed aspect, which could be done with something like a trend renewal process or a modulated gamma process. But here are some references, and thanks everyone for your attention, and I guess we can get the discussion started now.
Thank you very much, John. Thanks for your very clear presentation and a very clear paper as well. The paper was very interesting and very clear to me. I have a few, we had hoped to get Dr. Song from CDC to be the discussant, but he wasn't able to make it. So I've got a few things to discuss on the paper, which may be a little bit simplistic. I'm not sure that I got all of the points that needed. But in some ways, what we're doing here is we're looking at the regularity of a process of repeated events and trying to assess what you have called the coefficient of variation or the variance of the events and see how that might vary from one scenario to another. And these kind of events crop up all the time in testing for cancer, testing for HIV and other conditions. We're assuming then the events will follow some unobserved underlying process, such as a Poisson distribution or a gamma distribution for the negative binomial, or some other, as you mentioned in your last slides, some other distribution. Now, if we had the full event time for each of the events, so that we could do that, it'd be very simple to estimate that, because we could use the overall mean as the mean number of events, and the variance of that estimate of our regularity, as you said. But furthermore, as you say, both the mean and the variance may be influenced by covariates in different ways, both individual and grouped covariates. So in that case, as you did, we could introduce the two regression models, the regression on the mean and the regression on the variance or the shape, to estimate the way that these two will vary according to characteristics. Now, the interesting part of your paper is that instead of having the full time data, we only have binary data in which we have the answer to a simple question such as, have you tested in the last 2 months or the last 2 years or the last 4 months, depending on what the condition is that you're looking at. And so if you look at the data, that kind of data, we will just get the simple frequencies of how many people tested in each period, and that might be all that you want to know as a health planner, but it's not very interesting as a statistician if you want to know whether interventions work and whether they affect the regularity or the frequency of an event. And which interventions, which of these parameters do they affect as interventions? So you put forward 2 estimation methods there. One is the full likelihood method for looking at the time to the first repeated event. And we can only use that for the first repeated event because only the initial time of testing is known. I think that's right. And so if we want to use subsequent repeated events, then we need to use some kind of quasi-likelihood in order to look at all of the observed data. But then, of course, the times that we have are known with error. And the implications of this is that when we have more observed times, we have a greater number of periods observed, then we get a better estimate with the binary data when we use the quasi-likelihood methods for both the mean and the shape parameters. The quasi-likelihood method does have a larger bias, but in the end it has a smaller mean squared error because we're using more of the data. And as I've got a comment here, I'm not quite sure whether this is true. As the expected intervals get smaller, the estimation gets more efficient. I mean, that seems logical, and I think it's borne out from your simulation results. But I still think that we'd need to explore that a little bit more, and perhaps you could explain that a little bit more. You've used then these methods on a checking-in data, which is a small data set, I would say, only 600-700 people with only 12 months of follow-up. And so I was just wondering about the modifications that might be necessary if we've got larger data sets and we want to improve that model precision. And then I've got a couple of questions here. This is my last slide. The quasi-likelihood does better than the discrete event, single event, because we've got more data. But under what conditions? And what happens if we extend the period that we're looking at, or we're looking at larger data for longer periods of time? What about if we're using some kind of splines for changing effects for the impact of interventions over time? And that's something that another question that you've mentioned here is what happens if we use different assumptions, Weibull and log normal or log other distributions that we might have for time to event data. Can this be generalized to situations where the time to the first test, even the time to the first test is unknown? In other words, we might not know exactly when someone tested for the first time, which may be the case in a general walk-in clinic when we don't actually have a time to their first HIV test. How would you assess the goodness of fit of the two models against the observed population? And is it possible to estimate the continuous covariate from the binary model? Okay, so that's the limit of my questions. Some of them may be a little bit off the mark, but it's just a start for anyone else who wants to raise some questions. But first of all, let's see if John wants to respond to some of those. John.
Sure. Thanks, Jim. Those are some really good points, actually, especially this idea of the time, if the time of the first test is unknown. And that's kind of a situation where you might want to look at an equilibrium renewal process. So that's when you just start observing at a random time. And then, the time to the first event has a different distribution than the time between subsequent events. And we did think about this. The reason we focused on the ordinary renewal process as opposed to the equilibrium renewal process was because with our motivating data set, we did know that to be enrolled in the study, each subject had to start off with an HIV test. So everyone began the study with an event. So in that sense, they were all kind of at the same baseline level. So one of the issues actually with moving to an equilibrium model would be that it's harder to identify the the mean and the coefficient of variation independently because the equilibrium process would be stationary. So you don't have this idea of different proportions expected in each interval, which is what we use to distinguish these two parameters. So one of the ways that we thought of to deal with that would be to bring in the second moments of these binary indicators. So that would be modeling the correlation between the intervals, but that's a much more difficult problem analytically. So we haven't made too much progress with that. But in the case where with a walk-in clinic, hopefully you might have more exact information following them up prospectively. So one of the important aspects of these methods, I think, is that they can be applied to data that's possibly collected for other purposes or collected via surveys, which is a cheaper method. But it's as you said, Jim, it's easier to estimate if you do have these dates or times of events. And another good point, actually, just to kind of move to a slightly different topic here, but the notion of splines or something for changing effects over time. So that's something that we also thought was potentially useful and interesting, but that would be a violation of the renewal assumptions. So that would require us to go to, as I said, something like a modulated renewal process or a trend renewal process. And again, when we're already limited dealing with binary data, so it seems like it would be a bit of an uphill climb to incorporate something like that with such limited data. And in terms of goodness of fit, I think that the slide on that I showed with the plots is it's kind of it's somewhat of a ad hoc way to look at that, but it at least shows if you're mostly on the mark or not, and you can see from that slide, if I can just go back to it here. You can see here that the judging the observed data is the black circles, and the fitted model means are the open diamond and open square, and you can see that generally the forward recurrence method's closer to the observed data, and it does again have an overall lower root mean squared error. So I guess it's kind of hard to know how close is close enough. So that's sort of an open question that I think is interesting. So if anybody has thoughts on other ways to look at goodness of fit, that would be interesting as well.
Okay, John, thanks. That's a good response to a couple of my questions, and probably raises more questions with other people. We've got a couple of questions from the audience. Can we get them to ask you? I think we're going to start with Ola.
Okay.
Yeah. Ola, do you want to ask your question about bias?
Yes. I'm not sure if you missed part of the presentation. Thank you for your article. It's well written. I had a question on bias.
Okay.
In the article, you said you are estimating bias, and I want to understand more. What do you mean by bias, and how are you estimating them? My training says you cannot estimate biases, so I'm really interested to know how people can estimate that. Thanks.
Okay. So I'm not sure if I understand the question. So what? Sorry. Could you repeat part of that?
Okay. What do you mean by bias in your article?
Bias?
Yes.
So,
and how do you estimate them?
So, John, just to explain, Ola is a first-year PhD student, and she's really sort of like wanting to know some of the basic ideas about estimation of bias from your data.
Oh, so we're not estimating bias in the data. We looked at bias in the simulations. I'm not sure if that's what you're asking about.
Yeah, that's exactly right. So you're using the simulated data to, because you know what the parameters are in the simulated data, to see how far your estimates are from your real known quantities in the parameters. I think that's the sort of idea that Ola wants to get a hang of, and I think that's shown up in that figure that you showed earlier.
Right. Yeah. So that's true. And as you said, Jim, there was more bias with the quasi-likelihood showing up in the simulations than with the discrete survival likelihood. And we did look at that as well in simulations, and some of that bias is actually a result of the discrete approximation that we're using. So one of the theoretical properties that you would like to have, or that you need to have for unbiased estimation, is unbiased estimating equations. So the estimating equations have to have mean 0. And when we use this discrete approximation for the forward recurrence distribution, we have estimating equations that are somewhat biased. And we can remove a lot of this bias by increasing the number of partitions in the approximation, as I mentioned earlier in the simulation slide. But this does add computational complexity to the model fitting. So that's a really good point. Is just in terms of trying to reduce the bias, you can increase the number of partitions in the approximation.
Okay, thank you, John. I think Farshad was another one who had a question, or two questions, in fact. Farshad, do you want to ask your first question?
So I think I see the questions in the window, the chat window here. Is the first question, why is the model based on the coefficient of variation?
That's right.
Okay.
That's the first question Farshad had.
Yeah, so that's another good question. So the coefficient of variation, we really wanted to separate the notion of frequency from the notion of regularity. And if you just look at the mean and variance, then the variance is going to be larger or smaller depending on the mean. So if you had really infrequent events, then that's a large mean time between events, and you kind of expect that also the variance might increase in proportion to that. So we wanted to look at something that was, in a sense, normalized by the frequency, so that we could remove that part and just look at frequency and regularity independently. So the coefficient of variation is just the standard deviation divided by the mean. And so that's why we looked at that. And it's what's nice about the gamma distribution is there's a very simple relationship between one of its parameters, the shape parameter, and the coefficient of variation of the times between events. I'm not sure I understand the second part of the question, which is about precision. I guess with binary data, we're a lot less precise than if we had continuously observed data or even count data. In the paper, we look at simulations where we do have kind of the baseline case of continuously observed data, and we did see that precision is a lot more affected for estimating the regularity parameters. So the parameters pertaining to the shape or the coefficient of variation of the model. Because that's kind of related to, again, these sort of second order, second moment properties of the inter-event distribution. So we saw a lot more loss of efficiency on those when we have binary data compared to continuous data than we did in terms of estimating the frequency of events or the mean time between events. So the second question, if the mean and variance are not independent from each other, what's the main effect on the gamma distribution in this model? So the gamma distribution has two parameters. So you can always reparameterize it in terms of mean variance if necessary. But I'm not sure if this is getting at sort of the notion I mentioned a moment ago about, that's why we looked at the coefficient of variation, because it is, more independent of the mean. In terms of the gamma distribution specifically, I think we could look at other distributions, and they have different relationships between, their parameters and the mean coefficient variation. But something like the Weibull distribution, I think, has more complicated expressions for its moments, which is one reason we didn't focus on that. And again, the gamma distribution has some history in the literature on sort of coarse and recurrent events data. So that was another reason we focused on that.
Okay, thank you very much, John. That's good. Just asking if there's any more questions. So in some ways, having these one regression equation for the mean and one for the shape, you allow them to be correlated with each other. You allow for the fact that there's correlations between the two, and you allow for independent estimation of the mean and the shape from your data, so that you can. And I think in your example, you showed that the intervention had greater effect on the shape, but didn't change the regularity or the frequency. Is that right? The frequency.
So that's a good question. Just looking at this slide with the parameter estimates, the shape parameter was actually found to be significantly different between the two intervention groups by both methods, but the frequency was only found to be significantly different by the forward recurrence method. It was, the p-value for the discrete survival method was about 0.1, where it was less than 0.01 for the forward recurrence method. So again, what's kind of interesting about this is that the direction of the effect is maybe contrary to what we would have hoped for, because really, what we'd want to see for HIV testing is improved frequency as well as improved regularity. But what we saw for the SMS group was improved regularity, but lower frequencies of testing. But again, I think that's one of the nice features of looking at both these parameters and modeling them both as functions of the covariates, is that you can answer these questions independently instead of kind of just only looking at frequency, which I think is kind of broadly been the approach with recurrent events methods previously.
And did you find that some characteristics were associated with frequency, and some characteristics, not the were associated with the regularity, so that you could identify different characteristics that were associated with each?
So we could have, and we did fit some models with more demographic characteristics, but I'm fairly sure that I don't have those results in front of me. I think they're in maybe the web appendix for the paper, but I don't think that any of them were significant. So it doesn't seem like things like education level or race or ethnicity. I think we had another one in there, but age, I think. It doesn't seem like from this data set that any of those really had much of an impact on either frequency or regularity. But again, I want to stress that this is, as you said, Jim, kind of a moderately sized sample, and with binary data, we might just not have the sample size or the precision that we would need to detect those effects.
Yeah. So I think related to that, Ola has a question about what kind of data you need, and if you collected larger amounts of data, what you would do with this. Ola, do you want to ask your question?
So I think I see it in the chat window here.
The conference has been unmuted.
Can we use the method to estimate recurrence of CTC visits? Sorry, what's CTC?
CTC visits are visits where people come for collecting their antiretrovirals. HIV-positive patients will come supposedly every month to collect their antiretrovirals, or every 3 months, depending on their stability. So can we use it to assess the frequency of visits to the clinic to collect their treatment for HIV?
Yeah, that's a very good question. So that's something that's supposed to occur every month, and you want to look at the frequency and regularity of that, because ideally, people would be coming every month. So that's I think that would be a really interesting application of this, because it's almost already kind of binary data. So by the month, did somebody or didn't somebody come in to get their antiretrovirals? It sounds like you might have more detailed data, though, if you have dates of when they came in, because then you have you can use you can use some other methods to estimate more directly the mean time between events and the variance of the time between events. And this is something that we've kind of thought about a lot in terms of how discrete does the data have to be to be considered binary data, and does it make sense to look at the level of days? And I think in this case, again, I guess I would consider the intervals for the binary data to be months, and then whether or not somebody had come in to be your outcome. So I think that would be a very interesting application. And again, as I said, I think you could look at both that using our methods, and if you had the dates of people's visits, you could look at using the continuous data to estimate those parameters as well, and see if there's agreement or not. And I think that would be really interesting.
Yep. So you could assess how well the methods work with some real data. Yeah. Okay. So perhaps that's an idea for Ola to collect some of that data. Okay. Innocent had a question about software that you might use.
Yes.
Innocent.
So I used R for this, and I think we made the code available. But if not, I can share that as well. The tricky part is just that discrete approximation for the forward recurrence times, because I think it's a recursive algorithm that we use for that. So.
Yeah, and we're encouraging people to use to use tidyverse and things, so that make it much more regular packages in R. Did you use what packages did you use in R?
So I'm not sure. I'm honestly not sure I used any particular packages. So ultimately we were optimizing either the discrete survival likelihood or the forward recurrence quasi likelihood. So I used Optim, which is just in base R, to do that. And again, the discrete approximation, I had to code that manually. So I don't think I don't know that I used any particular packages, but yeah, there are certainly some that might have made some of the coding easier. But.
Okay, but the code that you've written would be available if someone wanted to use it in, say for instance, Ola wanted to use it in some of her work.
Yes, absolutely, and I think it might be available with the online supplementary material for the paper. But again, if not, I can share that.
Okay. So you might get a few students asking you for some code in there after this.
Sure, great. Happy to share it.
Good. Okay. Anyone else got a question? Oh, Innocent's got his hand raised. Innocent?
Yeah. So I am thinking here, for example, in the context of survival analysis, I have a problem, for example, where we are working with the birth registry, where, for example, mothers have deliveries, let's say 1, 2, and more deliveries, which are all clustered within a mother. And these deliveries are not happening at regular time intervals. There will be different time intervals for deliveries between mothers. So I am asking myself, are we going to apply a similar approach, or we can just use Cox models in predicting outcomes at different different spaces? Given that, for example, we have a binary event like death, and we have a longitudinal nature of this data set.
Right. Yeah. So that's a good question. That's another. I think this might be another situation where you would have access to the actual times or dates of the deliveries. So you might be able to use methods for continuously observed data.
Yeah.
Yes. If it was to do with the delivery, but it might be with recall bias. It might be that you're asking about an event which is not exactly known. I mean, it might be sort of sometime.
Yes, that's a really. I didn't understand that this was kind of a recall situation. That's a really good. That's actually a really great use for these kinds of methods. And we've looked not necessarily this exact method, but if you're asking about the time since somebody's most recent delivery, okay, then that would be something that I think it would actually make a lot of sense to use a discrete model for, because as Jim said, recall bias could be a problem. So you could just, kind of discretize their response into, was it within the past year, within the past 2 years, or, you could think about different gradations of that as well. And then you could use, again, the same kind of parametric approach as we use to get the backward recurrence time distribution. Again, assuming that the times between the deliveries are from a renewal process. But the idea of discretizing it instead of using somebody's exact recollections would be that you could hopefully minimize the effects of some of the recall bias, because you're looking at, it'll be accurate it'll be accurate as an estimation method if their recall, even if they're off the mark, if they're still within the correct kind of interval, then that should help you with bias in your estimation. So I think that would be a really interesting use of this kind of model. Yes.
Mm. And something just also about things like sexual behavior history. You ask someone when did they start a sexual relationship, and they might say, well, it was 6 months ago. Again, it's the kind of thing where you might discretize that, and it might give you a better opportunity of estimating it than trying to get the exact date from the person.
Exactly. Yeah, I think that's very true. And a lot of the applications that we see for these kinds of methods are with kind of surveys like that, where you would be asking, because what we've seen in some other circumstances is, surveys that ask, not necessarily longitudinally collected, but if you ask at a single time point, when was your last HIV test or sexual encounter or whatever, they actually only give them the options of things like within 3 months, within 6 months, within a year, or more than a year ago. And again, that's kind of it's probably a more difficult problem for some sort of non-parametric method. But with these parametric methods, there's a really there's fairly simple expressions that you can get using renewal theory to estimate mean time between events and coefficient variation. And you could certainly, parametric assumptions might be limiting, but you could try different parametric distributions, and we presented one option for how to assess goodness of fit. And actually, I think if you only had data at one time point, you'd probably actually be able to get a likelihood function. So that might make things even easier. But yeah, so a lot of the ways this comes up is in these surveys that ask these questions discretely. And another of the extensions that we've thought about is what are the optimal intervals to ask these questions in order to minimize the variance of your estimators. So that gets into questions of kind of optimal design for these survey questions, which is another kind of interesting area.
Yeah. So you've used your methods with survey surveys and survey questions in the past, have you? Or is this something which is still being developed?
So the data that we analyzed for this paper was actually survey data, and not in the sense that I was just talking about, but that what I am talking about is something that we're working on now, and that's again at a single time point. They ask the subjects. I think they do ask them when their most recent HIV test was, and they have the options of I think it's within 3 months, within 6 months, over a year or never. So that's the work that we're doing with that actually is using a different question, which is lifetime number of HIV tests. So that's hopefully a bit more informative because then you have a count outcome, and then you can look at the time over which those tests occurred because you also know the age of the subject, and then their age at first sexual activity, so kind of the time that they became sort of eligible to test for HIV, and you can use that to get some other estimating equations to again estimate. In that case, we're not necessarily relying on the parametric assumptions, but yeah, that's some work that's ongoing.
Okay, so that's so that's a slight extension to this in the use of the counts as well. Yeah. Okay.
Right.
So just a quick question. Anyone have any final questions for John and to just about his question? You've got a couple of minutes left. No more questions. We've got a couple of people here. No questions here? Okay. So if not, I'll hand it over to Christy, who will wrap up and tell us what the next steps are. Christy.
Sure. Thank you guys for joining us. We were happy to have you. It seems like a very great discussion. We want to remind you that the next Journal Club is on December 13th. Our presenter will be Shu Yang. You can find out more details about this on our website, biometricssociety.org. If you have any additional questions, you can reach out to us via email, and we will be in touch soon with the audio and presentation for you to review again. All right, thank you guys, and have a nice day.
And thank you very much, John. Yeah, thank you for your presentation. It was very informative.
Yeah, thank you, Jim, for inviting me. I think this is a great discussion.
Okay, hopefully people will get in touch with your need for code.
Yes. Do they have my email address or?
Yes, I have it. And I think
Thank you. Please stand by.